Alright, so in this video I'll be looking at the 2009 British Informatics Olympiad Round 1 exam, question 3. This question is called Child's Play, and this is a great example of a question which seems difficult at first but can later be simplified. So let's jump right in. Alright, so the question states, a toy set contains blocks showing the numbers from 1 to 9. There are plenty of blocks. We can just take that to mean infinite of every block, or we will never run out. Showing each number and block showing the same number are otherwise indistinguishable. We can consider the number of different ways of arranging the blocks so that the displayed numbers add up to a fixed sum. For example, suppose the sum is 4. There are 8 different arrangements. 1, 1, 1, 1, 1, 1, 2, 1, 2, 1, 1, 3, 2, 1, 1, 2, 2, 3, 1, and 4. I mean, at first this might seem a bit arbitrary, but we'll look at this later. These have been listed in dictionary order, just like in a dictionary where all words beginning with an A come before those that begin with a B, and all those beginning with AA come before those beginning with AB. We have listed the origins beginning with a 1 before those with a 2, and those beginning with a 1 then another 1 before those beginning with a 1 then a 2. Alright, so it's saying you're taking it like a dictionary, except instead of letters you're using numbers, and 1 is lower than 2 is lower than 3, so on. So, onto the question. Write a program to determine the nth way of arranging the blocks to make a fixed sum. The program should input integers s and n. You should output the nth way of arranging the blocks in dictionary order to make the sum s. You will not be given n that is greater than the number of ways to arrange the blocks, so there's no need for error checking, so we can ignore error. Ignore this error. Alright, so let's head over to a whiteboard and let's see what we can make of this. So it's always good in these problems to try out small cases and see where it takes you, especially if you're working with question threes, which are generally algorithm questions. Okay, so let's say we are representing the sums 0, 1, 2, 3, 4, 5. Now the sum for 0 is just going to be no blocks. It seems a bit useless, but we'll get back to it in just a moment. The sum for 1, there's only one sum for 1, and that is with 1. And notice how I'm representing these as strings. And that will also become important later when we move on to how we're actually going to code the program. For 2, we can have the arrangements 1, 1, and then 1. For 3, we can have 1, 1, 1. Oh, sorry, this is meant to be a 2. 1, 2. Then we can have 2, 1. Then we can have 3. And notice how 2, 1, and 1, 2 are counted as different options. Like in the question, you can notice how they had 1, 3 as different to 3, 1. So order matters, in a sense. So the order of the blocks matters. It's not just about the counts. Alright, so now we have this 4 column, which you already have filled out for us, which is 1, 1, 1, 1, 1, 1, 2, 1, 2, 1, 1, 3, uh, 2, 1, 1, 2, 2, 3, 1, and 4. And this gives us 8 possibilities. And we could say the sequence continues then on from 5. Alright, So now what we can do, we can count the total number of possibilities at each stage. For 0, there's just one possibility, which is no blocks. For 1, there is just one possibility, which is one block, which has a value of 1. For 2, there are two possibilities. For 3, there are four possibilities. For 4, there are 8 possibilities. And at this point, you should be alarm bells should be ringing in your head. You have 1, 2, 4, 8. These are the powers of 2. So this is 2 to the power 0, this is 2 to the power 1, 2 to the power 2, and 2 to the power of 3. I mean, this doesn't initially tell us how we're going to solve the problem. So let's look a bit more closely at a couple of specific examples. Specifically, we're going to look at changing the values from 0, looking from transforming the values from 0 to the values to 3. And we can get rid of this for now. We can get rid of the powers at the count. So firstly, let us consider the ways to transform 0 to 1. This is really, really basic, simple. There's no need to overthink it. Oops. You just, from 0 to 1, you just add 1 onto the front of whatever you have for 0. For 2, what you can do, you can take this 1 and place a 1 in front of it. This 2 then is produced by taking this empty string and placing a 2 in front of it. This 3, these two possibilities look very similar to these two possibilities, except they just have a 1 in front of them. So what we can do, we can say this has transformation of 1, so adding 1 to the front, and this transformed by adding 1 to the front. Now, 2, 1 isn't immediately explained from the values for 2, but if we take a step back and look at the values for 1, well, then we can see that this is just 2 with this 1 after it. And once again, for 0, we add 3 in front of it. And if you've done these types of questions before, you can kind of, you should be able to see where I'm going with this. This is recursive. In other terms, each term n is dependent on the terms before it. For example, we can see that 1, 1, 1 is based on 1, 1, which is based on 1, and that's based on the empty string. And what we can do then is to say, it's time for dynamic programming. This really just, and drawing the diagram like this, rather than just thinking about the problem, allows you to see, oh, we can construct everything using our base cases. And in this case, it's probably easier to think about anyway for me if we take 0 and 1 as our base cases. I don't know, I just prefer it like that. You can just take 0 as your base case. Um, but having decided that, let's think of our strategy. So our strategy is going to start off with, we input S, and this is going to be the number we're searching for, right? So this number is going to depend on the values s minus 1, s minus 2, all the way up to 0. So what we can do, we can define our dynamic programming array, which I'll just refer to as a DP, using our base cases for 0, which has uh, only one possibility, which is just the empty string, and 1, which just has one possibility, the string with just 1 on it. And now what we can do, we can say, okay, so we iterate from values of 2 all the way to s. And what we say is calculate all the terms. So firstly, we can take 2, and let's just do this off to the side a little bit. So we can take the term 2, and 2 is now going to be based on this term here and this term here. So that is going to be equal to, the possibilities there are equal to 1 plus 1, and then also is equal to 2 plus 0. And the next key step is just seeing that you can calculate this by the difference between that is just going to be the difference between whatever value here and whatever value we're iterating over. So, in fact, we're going to need a separate iteration here. We're going to need to look at from values of this, whatever this is, let's just call it x to 0, and we're going to step backwards, going down. And the reason we're going to go down here is because, well, as you can see in this case, adding 1 to the beginning of a number is going to make it higher in the dictionary list than adding 2 to a number or adding 3 to a number, etc. So therefore, we have to take the very previous term first. So that's why we're stepping down. So we take the values from x to 0, and this is not including x, because otherwise, because there's no currently defined values for x, so just not including x. And then what we do there is we say get current values, add the difference to as the first character, and then append it to our DP at position x. And that pretty much solves it actually. From here, there's not much left to do because you have your array and it shows you all the, and then it's just a list of sequences, well, at the particular point s. So at dp of s, you will get all the sequences for s, and all that's left to do is index by n minus 1. And you'll notice that I use n minus 1 rather than n here because arrays are 0 indexed, whereas whereas when they input n, they're asking for the nth possible, the nth possibility. So that's going to be indexed of 1, indexed by 1, nth way of arranging the blocks. Okay, and yeah, that's literally the whole program. That's all we're going to write. And here it is. It's 13 lines long, and that. This is enough to solve the problem. The first line is probably the most confusing to understand in all of this. Um, this is just in Python. The map function in Python allows you to take a set of values and convert. Well, you can use it in this case to convert each of them to integers. And what I'm doing here is I'm just splitting by space to so that I can split S and N in the input because you will notice in this input that there's 4 space 5. Okay, so S and N are we are then extracted from whatever list we get, and from there we just follow the logic I've just talked to. You have your dynamic programming array, you have your for loop, and you here I just create an append array and appends to this append array. What this is just this just represents what the set at S that I'm going to append to. Well, like at this position, for example, at position 2, I'll have this array. Rather than initializing the array and then appending directly to it, I just create this and append it at the end. So we do that all the way from 2 to S. The range function in Python doesn't include the last value, and then we print uh, the what's at the index S, so all the list, and we take the n minus nth value. So that's going to be the n minus 1th index. And that's it, that works. So if we run it, for example, what we will see is that we input 4, 5, and we are given 2, 1, 1 as our output. Uh, there is also another way to solve this. I found this out fairly recently. If you don't already know about it, there's a GitHub repository run by a guy called SpookyL. Oh, uh, and he publishes, oh dear, he publishes solutions to the British informatics problems, and they're actually, and then in his solution, he gives a different answer completely. He uses direct recursion using something called an LRU cache, and you could search online what that means. And his solutions are also a good way of looking at some of the problems, um, and just show different ways of solving them. So I definitely recommend you to check that out. Here it is. Yeah, so this is his repository, and I'll put a link in the description. If you go into code, you should be able to see for the 2009 paper, question 3, his solution is uh, uses a slightly different method. The essence is pretty much the same, that you can construct your later terms from your previous terms, and here he just directly uses a recursive function. Hope you enjoyed watching this video. If you have any suggestions on which questions I should do next, please keep them down below in the comments. Thank you.